In this talk I'm going to revisit a very old subject, that is to say the outphasing RFPA, that meaning RF radio frequency power amplifiers. So pardoning the pun, I'm sort of really just trying to sort of take a new look, which is what I have been doing at Cardiff in terms of revisiting the subject and sharing some of that with you. Talking ancient and modern, as I say, it's something that is very old and something that we have been revisiting recently. Ancient because the original paper, which is normally attributed to, most people normally consider to be the original seminal paper on this subject, was written by Chireix, I assume it's a Frenchman. He sort of wrote this paper. I think those of you who are aware of it, this is just a copy of the first page, or some of the first page. This was published in the Proceedings of the Institute of Radio Engineers, so this predates IEEE. As you can see, the date November 1935. And interestingly enough, it was called a high power outphasing modulation, because I think this is the first thing one realizes about this technique. It's not really an amplifier, right? You know, you do not make an outphasing PA as we now call it, and you have sort of an RF input and an RF output. That is simply not the case. I mean, it is actually it is a modulator in its own right. So that's the first point. Let's just go back and talk about a few things. I think over the years, over the decades, I'm not really sure, and I'm always glad for somebody to email me or ask a question or shoot me down that this is wrong, that whether there is really any significant, substantial, actual implementation of an outphasing Chireix type PA. Plenty of research papers, no question about that. Plenty of research papers. They seem particularly keen on this in Canada for some reason. There are quite a few groups there, not in any way being detrimental to the very good work that's been done there, but in general, lots and lots of plenty of research papers. I'm not too sure whether there's actually been much in the way of actual implementation. And I think the reason for that is that a lot of people do go straight back to the original Chireix paper, and first of all have a great deal of difficulty following it. Of course, it's very much aimed at vacuum tubes. A lot of the terminology and the way even people used to do circuit analysis and so on is somewhat different in such a long time ago. But the things that you kind of tend to sort of realize and maybe have some doubts about, first of all, the active devices are assumed to be voltage sources, and this is certainly always a concern. You know, we tend to think of transistors usually as being current sources, so you know that's a first question. Those strange shunt reactances, this is not terribly well explained, I don't think, in the original paper, and this is something that I certainly wanted to revisit a little bit here. The third thing is this business about power back-off and drive, power added efficiency issues. It seems to me even in some of the more recent, a lot of the sort of, let's call it the modern era work that has been published, okay, we understand the basic idea is you have these two inputs which are maybe at constant amplitude, but they have, as you vary the phase, the output varies and the efficiency remains more or less constant for certainly a range of outphasing. Say you take your normal classical 6 dB back off to compare it with something like the Doherty PA, you sort of basically offset the phase of the two inputs so that you get 6 dBs less power. And if you get things right, according to Chireix, and indeed as I'll show you, it does pretty much still sort of survive modern treatment. Yes, in principle you do maintain reasonably constant efficiency over that 6 dB back-off range. The problem is that you're still driving it with the same signal, the same drive power that you were for the full output, and that is a bit of an issue. We really need to back off the drive power in order to preserve our power added efficiency. Obviously, one of the reasons that it has sort of had something of a rebirth or a renaissance in the last decade is because obviously the availability of digital signal processing has certainly enabled the possibility of realizing some of the functions, particularly this phase control on the two main inputs using modern digital signal processing techniques. Devils and details. My own experience of this in terms of actually implementing an outphasing system, the devil does really lie in the details. You know, it is a whole different kind of an animal that you have created, and it has all sorts of quirks and characteristics that are unfamiliar when you're used to dealing with a straight RF in, RF out kind of a system. So in terms of the modern era, I suppose the question I'm sort of perhaps still asking myself in my own research group is, you know, what is actually left? You know, I mean, there has been a great deal of research work published in the last sort of few years, last 10 years. You know, one has to keep asking, you know, is it just one of these things that was, is, and always will be a technique of the future? Perhaps, maybe not. I think particularly one thing that I myself always feel quite strongly about is that there has to come a time when what I call dual input is acceptable. Unfortunately, my experience right at the moment is that having the idea of having to generate two signals whose phase and amplitude have to be controlled according to sort of given rules and regulations, calibrations, that is still very unpopular. I think system integrators still like the idea of their RF output device, the thing that generates the power, has to be a box, you know, with an input connector, an RF input connector, and an RF output connector, and that's the way they like it to be. But I think as we move on, as communications systems get more complex, I think that not just dual input, but I think multiple inputs will ultimately become acceptable, and I think that is perhaps when the outphasing, that's when the Chireix configuration time may finally arrive. I hope it will not reach the centenary by that time. I certainly won't see it myself if that's the case. One of the things that I've been really trying to focus on here is the, what I call a waveform engineered approach. That is to say, to try to take this system and to understand what needs to be done in order to generate the right kind of waveforms to maintain efficiency and power. So that's the original paper. This is, I think, an extract from this is actually the curve here, the red curves are an extract from that paper. I think you actually find those two curves in the paper. There is, as I've already referred to, these mysterious reactances that are not really all that well explained. And this is where I think, certainly I myself, when I first started reading and trying to understand the Chireix technique, I did view it as simply an outphasing system. And you know, what you find is that as you outphase, as you controlled these two phases and two voltage sources, you actually generate a reactive component that is itself dependent on the outphasing angle. And you try to basically tune that out. So you get this sort of floating reactance that you can tune out at a selected point in the power back-off range. Now, of course, we're not here talking about power back-off in the conventional way. We're not here talking about backing the power off of the drive. When we talk power back-off in an outphasing system, all we're talking about is literally offsetting the phase to get less power. And that's a whole different thing. But basically, if you follow, as I say here, this mysterious compensation reactance, you choose the value. In this particular case, maybe we might choose this value of 3 times R. These are all normalized values, which I don't think I need to explain, or at least I don't propose to. There is some value that you can design to that will give you this efficiency back-off curve as you control the phase offset. But unfortunately, there are quite a number of assumptions along the way, and I don't think anybody that I'm aware of has really ever sort of published a power back-off, an outphasing power back-off like that, although admittedly we are perhaps starting to get closer to it. For comparison, you see, we're actually showing, and it's not an entirely fair comparison, and I think that's an important point to make. If you take the same devices, if you like, the same transistors, and make a Class B amplifier, this is the back-off characteristic you get. Obviously, a much faster back-off of efficiency with power. And even the Doherty, although the Doherty PA maintains its efficiency for this upper 6 dBs or thereabouts, we still sort of don't really quite seem to get quite the same stellar results that this would appear to give us. But there are numerous assumptions along the way, and I think it's fair to say, certainly at the 80% level, I think that these curves in particular, what we're doing here is we're comparing something that is a little bit too idealistic. So let's just look at the outphasing circuit. Basically, what we do, and I think this you can just about glean this out of the original paper by Chireix, although I've sort of translated it here into somewhat more modern terminology, modern analysis methods. What we have is we assume we have two active devices that behave as voltage sources, and these V's and I's, of course, are all complex quantities. They're complex numbers. They have magnitude and phase. So the one here on the right, we put a phase offset by multiplying it by e to j phi. So phi is the outphasing angle. We can then perform actually what would appear to be a fairly straightforward piece of circuit analysis. We have these shunt reactances, which for the time being I'm just simply calling x1 and x2, and then we have what in this configuration has to be a floating load resistor. Obviously there are things we can do about converting a floating load into a grounded load. That's a bit of the devils and the details that I referred to earlier on. So if we do this analysis, basically we are assuming the active devices behave as voltage sources. We're going to say quite a bit more about that in due course here, but suffice it for now to say, well, if these are transistors, field effect transistors, if we are, say, assuming that they stay in saturation throughout all of the conditions that we consider here, then we can assume that the voltage does remain more or less constant, so long as the devices do remain in saturation. And as I say, these shunt reactances, in fact, do actually play quite an important role in the design, even though I think their function was certainly not that well explained in Chireix's paper. I don't want to keep getting on at Chireix all the time. To be perfectly honest, I think even some of my own sort of courses and notes and so on, perhaps I've followed the same path and only relatively recently decided that wasn't really quite the right path. Not wrong, but I think to see what these reactances do, it is better to do this analysis to proceed along the present path. So this is not any longer Chireix outphasing. We're trying to generalize things a little bit. We're saying, well, okay, if we do the analysis in terms of admittances, we get these two expressions for the admittances that are being presented to each device. And of course, they are different. And what I'm showing you here, without getting too much into the details of the mathematics, I just really want to show you that there are fairly simple, compact mathematical expressions can be derived. Obviously, both the real and the imaginary part at each device is a function of this outphasing angle phi. Obviously, we know that. It is the imaginary part, however, that is a function of the shunt reactance. Maybe that's not too surprising. And then obviously the real part is both the real and the imaginary part, of course, are a function of the load resistor value R. So you can sort of quickly eyeball those equations and see that probably the condition that x1 and x2 have the same magnitude but opposite sign is going to be a condition of some interest. That gives it a nice sort of symmetric, or let's say anti-symmetric appearance if you make that substitution into the reactive components. And then we can actually normalize the whole thing. We sort of realize that in actual fact it's the magnitude of the reactance X in relation to the load resistor. We just normalize that, normal procedure. But the key thing here is about this page, this slide, we are already now seeing that the Chireix configuration, the outphasing, I say no more Chireix, the outphasing configuration is a load modulator. You know, I mean, that is the key point. That, you know, that there is this tendency to think that we're controlling the power because of the fact that we're offsetting the phases, and the phases don't add up correctly as you offset them. So we are controlling the load at each device, and this is illustrated in a more conventional way here on this Smith chart plot. What we're doing here is we're plotting the impedance trajectory of the two devices. Obviously there's two sets of curves here, and they are different. And what I'm doing here is plotting two different values of this ratio x over r, so that we've got a couple of different values here, and you can see that the value x over r equals 1, the specific case where we make the reactance equal to the load resistor, these two curves sort of touch each other here on the real axis. This is in fact normalized to r at the center here. So probably, and I think we already know here, we're starting now already to talk load modulation. I mean, clearly what we want to do, as pretty much with any amplifier configuration, it applies to the RFPA as well, even to some extent with an envelope tracking. What we're trying to do here is to move the load line of the device around, up and down, preferably up and down the real axis, and that's really what we would like to do. I mean, the ideal RFPA load modulator moves the impedance at each device plane, or the device plane if it's a single-ended, just simply moves it up and down the real axis in the manner that I'm showing. And even a factor of 2 is actually useful, okay? I mean, the RFPA basically really only does the load modulation over a factor of 2. So you can see that here, probably, you can now see, probably we do actually want to go to a slightly different value of this ratio x over r in order to get a little bit more sort of activity, if you like, along the real axis. Obviously, as we do that, we will incur a small amount of reactance, but nevertheless, in order to be able to, as we vary the phase, obviously we're going around these circles, in order to be able to move over a reasonable range on the real axis, we probably do want to overlap these circles a little bit, and that gives us a pretty good straightforward hold on the kind of value of x, the reactance, that we will actually use in our circuit design. It's just that you have to, of course, remember that one side is positive and the other side is negative. So when we say x over r is x1 over r, x2 over r is the negative of x1 over r, and so that one of them is ideally, one of them is inductive and the other is capacitive. So it is really load modulation that we're playing around with now. And of course, what we have to ask the question is, well, okay, in this configuration, how does this variation of the device plane reactance, let's supposing we are more or less moving up and down the real axis, you can see here that I've divided the Smith chart into two regions. Basically, on the left, we've got the unclipped region. That's the sort of lower impedance regime where the devices are really behaving as current sources, and, you know, the voltage is simply obtained by Ohm's law. Whereas on the right-hand side, we have got a completely different situation. We've got transistors that are saturated and therefore are probably operating at approximately constant voltage. But nevertheless, as we vary the resistance, again, Ohm's law applies. What we now say is that the voltage is more or less constant, but the current is approximately the voltage divided by the impedance. And of course, consequently, as we increase, as we move along the real axis in this direction, the load resistor is going up, so the current is going down, so therefore we are controlling the power. You know, we are actually modulating the load and simultaneously controlling the power. But the question really here is, do we really know in detail? And it's all very well waving your hands around and saying, well, a saturated device behaves as a constant voltage source. In actual fact, maybe that may not be really quite good enough. So I'm saying here, do we really know what happens when we hard clip our microwave devices? The LF here meant to be the low frequency fraternity, obviously for political correctness, I believe the female term is sorority, I'm told, I believe. The low frequency, people familiar with low frequency techniques will tell you that the efficiency contours in the clipped region, in the saturation region, tend to follow these Q curves. That is to say, the efficiency is perceived and can indeed be approximated to being a function of the Q factor of the load. So therefore, on the left-hand side, you get the sort of the more familiar looking efficiency contours. The right-hand side, things change rather dramatically because we move into the saturation regime, and these efficiency points here, as we cross over into the saturation region, they start to follow more closely the corresponding, the cognizant Q factor, the Q curve. So in actual fact, this is sort of, again, something that is not very well explained in Chireix's original paper, but he obviously is making this assumption. To my way of thinking, this is only really justifiable when you're talking about square waves. You know, if you have a square wave of voltage and a square wave of current, you can assume that the current is being clipped. It is still a square wave after it has been clipped. And as such, you can, in fact, come up with a reasonable, you can satisfy yourself that yes, indeed, efficiency will become a simple function of Q factor. So we don't have square waves. What we have is shown here. We have clipped sinusoidal type waveforms. That's to say, assuming we start off with a device operating in class B, that would be the current waveform would look like originally like the red waveform here. We have this sort of half wave rectified sine wave kind of current, classical class B current waveform. However, if we have got, say, for example, a sinusoidal voltage, let's assume that we have short-circuited our harmonics, then we will clip that current as the voltage, as we drive the device into saturation. What actually happens is that the voltage still carries on hovering. You know, the voltage never really reaches zero, but as we increase the load, what happens is that the device moves more into the clipping region, and you start to get these kinds of waveforms. The current sort of drops, but it doesn't drop in a sort of a nice, well-behaved way. It drops in this manner that is determined by its IV knee characteristic. So in order to get a more quantitative feel for exactly how the efficiency and the power vary as you vary the load in the saturation, the clipping region, we have to do a little bit of homework. This is a way that there are various ways that people use to describe the clipping function. This is a particular function we found to be fairly useful. It has this parameter n, and what I'm showing here is what this function will do. That's to say, if you apply it to a half-wave rectified sine wave, that's the red curve, what we get is the blue curve, because we are in effect multiplying it by this function here, which is plotted on top here. So these sort of dips here, these are the sort of the clipping. This is what determines the actual clipping of the device. It depends on this parameter n, which has typically quite a small value. It helps the mathematics if you keep its value to be an even value. But for a gallium nitride device, we find an n equals 4 or maybe n equals 6 gives you quite an accurate model of the clipping function. Just by way of showing you that this does actually work in the clipping region, what I've actually done here is the blue curves represent, what we're doing here is we're plotting power and efficiency contours for a typical gallium nitride device. That there is, in fact, if you want more details of this calculation, you can see the publication Transactions of MTT, March 2017. But basically this is what comes out of using that model is the blue contours. So the power contours are shown on the left here, the efficiency contours are shown on the right, and you can see that the measured values are the red curves. And basically the red curves are well to the right here of the high impedance range. So, you know, what we have here is a device that is well into the saturation region on the right-hand side here, and you can see that we are in fact able to model the power and the efficiency reasonably accurately. So this point we're making here is that if we start off with a class B device and we have a sinusoidal voltage, the clipping is significantly different and will behave significantly differently from the sort of classical behavior that we're showing on this slide that we've just seen. So that's just a point that is worth making here while we're talking about this. This, of course, is a class B waveform. The good news here is that although this clipping does reduce the fundamental component and does also reduce the DC component, so the efficiency isn't reduced as much as the fundamental. So that's slightly better news. The good news, however, is that the second harmonic is significantly suppressed. When you are clipping a current waveform just in the manner that I'm showing here, that's to say when the voltage is dipping fairly significantly, as you can see, into the knee region, this blue waveform actually has a second harmonic component that is crossing zero. So it is actually possible to have a set of waveforms that I'm showing here where the second harmonic component of voltage is essentially allowed because of the fact that the way it's clipping the current waveform, we are actually nulling out the resistive component of the second harmonic. So when we do this, we can see a substantial improvement in power back-off efficiency. And these are the sort of waveforms that we're going to be encountering when we try to make, or at least we certainly try to make these waveforms. In particular, I think what this is showing is the value of trying to use some second harmonic when you're designing outphasing amplifiers. So, for example, if we can make the second harmonic reactive, you can see a similar improvement in the power back-off efficiency, but the impedance environments can be matched up with the outphasing load modulation. This is what we're really doing here, is we're sort of saying, well, we're taking some waveforms which have got second harmonic components, and we're trying to match those up with the impedance trajectories that are given when we do outphasing. And that's what the result of doing that, in principle, is what I'm showing here in this slide. That is to say, if we stick with a sine wave of voltage, then what happens is that we're plotting here efficiency and power, how they vary as we sort of change the load resistor. That's to say, as we perform the outphasing, what we're doing is we're moving up and down the real axis. If we only have a sinusoidal voltage, we're following this blue curve. Now you see the blue is underneath the red and the green there, but the blue curve sort of follows this trajectory here. So we get this sort of loop, and we obviously see that the efficiency peaks here at about 65, the power peaks at a somewhat lower value of efficiency. That's what happens if we just simply short the harmonics and use a sinusoidal voltage. If, however, we pay more attention to generating the correct amplitude and phasing of second harmonic in an outphasing amplifier or an outphasing configuration, you can see that we can actually do quite a lot better. The interesting thing here is that you can see the red curve represents what happens when we add some second harmonic to voltage. So in other words, we're looking at these kinds of voltage waveforms, the somewhat more peaky kind of voltage waveforms, which inherently give us better efficiency simply because the DC component is a lower value as compared to the fundamental component. The point about this graph here is if you look that the red curve initially sits on the same curve as the original sine wave. That's because in this upper regime here, we are not clipping the current enough. So therefore, the second harmonic impedance is still registering as a negative resistive value. But we reach this magic point here. That's the magic point, if you like, that I showed before. That's to say here. We reach this point here where the second harmonic suddenly crosses zero and suddenly becomes a positive resistance value. So therefore it is a viable impedance level. And so all of a sudden now we can branch away from the original blue line, which was the sine wave, and we can really reap the benefits of having second harmonic component. So what I'm really showing here is that the modulating as we move up and down the real axis with the device in saturation, we are driving the device sufficiently hard, if you like, on the input to make sure that the voltage is already clipping. We're already into the clipping region at a level with the lowest level of power that we're operating. So that what happens is, as we move up and down the real axis, as we modulate the load, you can see that initially we're not allowed to generate second harmonic, but at this point we can start to generate second harmonic, and we can maintain this really quite high level of efficiency all the way down to maybe 10 dBs backed off. Now, all of this time, of course, we can significantly improve our efficiency with third harmonic. So in a sense, that what I'm showing here is the green curve represents the power efficiency contour for a class F amplifier. That's a much more familiar scenario where we are actually allowing the voltage to become more like a square wave, and also taking account of the clipping. We can of course get some improvement over class AB or class B. That's the green waveform. But as you can see, on the whole, it's the second harmonic voltage component that really enables us to maintain this efficiency down to a much lower level of output power. And this is somewhat further illustrated, really. What I'm showing here is we've seen the impedance trajectory. This is how we can generate these trajectories, by slightly overlapping these impedance contours here by suitable selection of these shunt reactance values. Those curves now, using the clipping model, there's quite a lot of work which I've not included. I say we have given a reference if you want to follow this in more detail. But there's quite a lot of work really in going from these impedances to incorporate the clipping model that we've talked about. What we end up with are these curves here. But I'd like to make it clear that there is a continuous mathematical path, if you like, going from here to here. I've not included any of that mathematics. It is in the literature. But the interesting thing here is that we can see how the amount of overlap here gives us a better power back-off characteristic. So, as I say, this looks a little bit more familiar. I mean, obviously now I'm showing you, particularly say this blue curve here, doesn't look too much different from the curve, admittedly, that we showed originally, that is derived from some of Chireix's work. But the thing that is quite a bit different is the efficiency levels. I mean, these are still fairly ideal kinds of devices that we're dealing with here, ideal circuits, you know, but we're sitting more at the sort of the 60% level, really, rather than the 80% level, in order to get these results. But for sinusoidal voltage clipping, the efficiency is quite a lot lower than is often assumed. Just a quick simulation, just by way of showing that this sort of thing can be achieved in practice. This is an actual circuit. I've got some, these are actually some using some device models, and so these are real transistors, is what I'm really trying to say, albeit maybe not some of the more detailed models. This is a sort of a standard CAD program library model for the transistor. But it has a real IV characteristic. That's the key thing. And as you can see, the combiner is also fairly ideal. I'm showing here an ideal combiner. We tend to think of balance, of course. We have this floating RF load, which we need to somehow get back to ground again. Now, obviously, in practice, you'd have to do that with a balun. And obviously, there's been a multitude of large literature on that subject, making baluns. In this particular simulation, I am doing it in a rather ideal way, using an ideal transformer. But the point is that if we do this simulation with a real device, we do in fact see very much the kind of characteristics that we have been predicting and certainly the power back off here we're seeing, you know, maybe pushing 10 dBs, but of course let's not forget that there is this PAE issue. This curve here, which time and again I always see in the literature, people show you this curve and you think, hey, isn't that great? You know, well, unfortunately, it's not great if you back off here, what, maybe 8 dBs, I'm showing you the 8 dB back off point there. It's not great. You get your sort of 65% efficiency at the 8 dB back off point, great. But you see, that is really not correct. It is not really correct to talk back off in a outphasing circuit. It's 8 dBs of outphasing would be more accurate, because our drive power all of this time is staying the same. When I plot this curve here, I am not changing the drive power. We're not backing off the drive power. And I do feel this is a very weak area in a lot of the research that I've done. Not by any means saying that it is a weakness shown by all workers in this field, let me hastily add, but it is certainly something to be very much aware of when you're reading papers, listening to papers on this subject. What we have to do is actually, and I'm going to skip a slide here, is actually to literally back the drive off. Now, fortunately, it turns out in this particular simulation, it seems like you can do it and get away with it. The point being, you see, that as we back the power off, if I go back to this slide here, as we back the power off, we are traversing the real axis, of course, in that direction. As we go backing off here, as we reduce the power here, what we're doing is modulating the load to a higher value. So in other words, we're going along the real axis in a sort of in a right ways direction. You know, we're moving to higher values of load as we outphase the power. So therefore, what we can say is, well, in actual fact, we can get away with a lower drive level, because although maybe we back our drive off to a lower drive level, the current swing, of course, is going down, but because of the high level of the load, we're still in the saturation region. So we are still actually allowed to sort of call it a voltage source, simply because it's the combination of lower current and higher load resistance. We're still in the clipping region as far as the voltage is concerned. And in this particular case, you can see that these different loops here represent drive power back off, so that we are indeed able to maintain our outphasing efficiency power back off. Our efficiency power back off, we're able to maintain high efficiency, but at the same time we are also able to back off the drive as well, and you can see that the dots all sort of pretty much lie on each other. So this issue of power back off in this particular case seems to be okay. It's all right, you know what I mean? We are in fact able to back the drive off, but it is certainly something that you need to be aware of. So what I've really tried to do in this talk is to sort of really just put a slightly, hopefully, considerably more modern perspective on this circuit, in terms of trying particularly to explain what was, I think, quite a big disconnect. I think that there is still perhaps an ongoing disconnect between the original very elegant theory that assumes transistors are voltage sources and so on, and the practical limitation. And so that's really what I've been trying to do here, is to provide a sort of a more up-to-date perspective on this. There certainly appears to be a resurgence of interest in outphasing, I think mainly due to the ability to construct these input signals using DSP, maybe at baseband, but also the need, as I said earlier on in my first slide, the need really for dual input RFPAs. I think that this is something that has to happen, otherwise generating all of these signals, these two signals from a single input is complicated. It's not to say that people haven't done it, they have. There's been some very interesting work in that area. But it would certainly make our life quite a lot easier, I think, if the industry could start to accept RFPA as a dual input microwave device. So what I've also shown here is the fact that there is possibilities for a more comprehensive waveform engineered theory to take account of and design for harmonic enhancement effects in the output voltage. You know, there are still tremendous benefits to be obtained by allowing particularly second harmonic in the voltage waveform. The presence of this second harmonic, it changes the way the devices clip, it changes this clipping function on the current, and this can all be used to very good effect. The slide that I did just gloss over, I should just go back to. This is in fact showing you the input drive, how this thing does back off. So in other words, we're going along the real axis here. And you can see here that in fact, you know, these voltages we are indeed using second harmonic here. We have managed to design the circuit environment such that the impedances at the second harmonic, as well as the fundamental, are such that we are able to actually leverage this efficiency advantage of these sort of class J type voltage waveforms. But at the same time, understanding that the clipping that it applies to the current is very important in terms of defining what those design impedances actually are. So that's the end of my talk. Have a good time designing your outphasing PA.